Um, yeah, so hello everyone. Yeah, I mean, as the title says, I'm going to be talking about information theory and energy efficiency. Now, the general problem that, or the general motivation for this is that whenever I come to this type of conferences, I mean, it is very clear that neuromorphic systems are efficient in some particular problems, but the question then becomes, well, how efficient can they be, and how would we know that we've reached the limit, and how would we know how to design them? And part of the problem is that these systems are very heterogeneous. So you have different technologies and you have different problems. So, are you going to have to run the whole energy analysis to just be sure that you're reaching this efficiency goal? So I did what most mathematicians do, which is make the whole thing absolutely abstract and probably useless. But at least that way we can get a formalization or a framework to try to answer these questions, at least a beginning to do so. And I know that most of you have already probably heard or seen Shannon's theorems, if not professionally, at least during your undergrads. I just want to point out a few facts, namely that the key insight, which I'm trying to somehow reproduce in my very toyish models, is that the right language for information is to use symbols and probabilities, and that's somehow embedded into the whole thing. And the fact that reliable communication or reliable computation can work even if you have somehow noise or unreliable hardware. So in a way here, what I'm doing is repeating some of these two sort of theorems, but in a more neuromorphic friendly setting. Now, the main approach that the main approach to derive the easy version of Shannon's theorem is to basically take a code and say, well, I want to minimize its length, but subject it to the constraint that the code has to be decodable. So I should always be able to tell two code words apart, but otherwise just to minimize the length. And all I'm doing here is to say, well, what if my costs are not symmetric? So what happens if ones cost me more than zeros? And the rest is just technicalities, but that's the main idea. Now, to try to give an intuition of how you can think about this, I'll start with the combinatorial view. And the idea is that, well, if you want to, let's say that you're in a very simplified setting where you have a constant number of active neurons and discrete time and all that, and you want to encode, let's say, 125 symbols. Well, the first thing you need to make sure you have, it's enough symbols. So you need to have, your system needs to have enough neurons and enough active neurons to differentiate all of them. And the way that you can do this is by saying, well, I start with 0 neurons, and then I have only one symbol, and I can add 1 neuron. If I go down this tree on the left, I go down to the left, and then if the neuron is inactive, I get a 0. If it's active, I get a 1. And I can add another neuron, and then I go left or right. And basically, at every level, what you get is how many combinations of n neurons with A active neurons can you get? Or in other words, this is basically Pascal's triangle. Or if you're Italian, the triangoli di Tartaglia. And the main point is that you can add a gradient in this. So you can go and say, well, if I add a cost, so let's say every neuron, every time that I go down this tree, I add 1. And every time I add an activation, and I add another 1. Then you can have these sort of equal cost lines, draw them on the triangle, and then see where you get the lowest line that intersects the constraint of having that many symbols. And this is somehow similar to a classical paper on neural computation, where they were looking at the energy efficient. It's just that instead of, basically that was more for trying to infer some efficiency values, and here I'm just trying to think of it as a design problem. Now, this approach is not very practical because you're going to get stuck in to basically run very large numbers. I mean, for any real problem, you might have millions of symbols. So you can turn that into an analytical problem, and the idea is that you just go and say, well, I just want to minimize a cost given a probability of all my symbols, subject to the constraint that I have enough symbols. And then by using Stirling's approximation and Laplace's method, anyone who's taken statistical physics probably knows those, you can basically get an analytical solution. Basically you can get a solution that you can then plug into your computer and solve it by Newton's method or whatever your favorite approach is. Now this is basically the source coding. This just tells me that if I have a perfect noiseless system, I can encode that much code, that much symbols. But one has to also deal with noise. And here I abandoned all hope of trying to write the equations, because just reading them would take already 8 minutes. But the idea that I want to transfer here is that you can turn this into some sort of packing problem. Basically, you go and say, well, I have a certain number of neurons, a certain number of possible active neurons, and that gives me a volume. That gives me a number of code words. Now, every time that I send something, that I put something into my system, it has noise, so it's going to be perturbed. And that means that it's going to move around some area. And this area gives me a ball, or a radius, if you will, and I have to make sure that two different symbols do not cross. So that basically, if one is perturbed, it would not be closer to a code word that's not the original one. And then basically, this is what in combinatorial geometry, or more generally in different branches of math, this is basically a packing problem. It's a rather complicated one, and we don't have proper solutions for like how much packing you can get, but you can get some decent bounds, and you can find some codes that would approximate this, at least in theory. Now, this is fairly abstract, and there's obviously very few, it's not something that I had plugged into a chip. But it's not as limited as you might think. So I just want to go over a few things that typically people to whom I explain this mention. One is that if you have a neuromorphic system where you have negative spikes, or you might want to consider not only one spike at a time, but a time window where you can have 2 or 3 spikes, that is not a problem. You only have to add more possible symbols. So this Pascal's triangle becomes a Pascal's pyramid, or a multidimensional Pascal's pyramid. But the math and the analysis is exactly the same, has exactly the same shape. It's just that there's some more symbols. One thing that happens sometimes is that if you try it in a toy problem, so you go and say, well, what about this 125 symbol that I mentioned? Well, the analytical solution won't work, because it's something that works only when you have a lot of neurons and a fair amount of active neurons. So you'll get, basically the equations might tell you you need 10,000 neurons when you in fact need 15,000. Not sure if this is clear for everyone, but whenever you try to use information theory to do anything practical, you have to be careful with how structured a problem is. So if you're thinking of encoding positions, for instance, information theory does not necessarily have the notion of structure. So you might not be able to say, well, point A is close to point B. So that's something you can do. Another thing that typically neuromorphs and neuroscientists are very aware of is that neurons are heterogeneous, and that's okay in this framework. It just makes it more complicated, but it's something that you can definitely look into. With that, I would like to acknowledge some people who are open for discussions and who helped me somehow frame the problem appropriately, namely Jean-Pascal Pfister and Huyan Shen from the University of Bern, and Stefan Moser from ETH, and then the institutions who hosted me or paid me, namely the Institute of Informatics, the lab where I am from Benjamin Greve, and the ETH postdoctoral fellowship. And with that, I'm happy to take any questions.